In some cases, when we work with turbine, we don't always work with the saturated steam or superheated steam. Sometimes the steam is in a mixture with liquid water. In that case, we call it unsaturated steam. Uh, and then to be able to quantify the fraction of the liquid and the fraction of the steam, we use the quality of the steam, in which 100% is when we have all of the fluid is actually steam. So here alpha uh, is defined as the dry fraction in saturated steam. When you have a stream with alpha equal to 1, basically means you have no liquid water in the stream. So when we have unsaturated steam, we have to take into account the alpha factor in calculating the enthalpy. So in this case, we see the enthalpy of the mixture of fluid and gas. Fluid here basically here is liquid, water and gas. That is equal to alpha, basically the fraction of the steam multiplied by enthalpy of the steam, saturated steam, plus 1 minus alpha times the enthalpy of the saturated fluid at given temperature and pressure. The same with the enthalpy, we also do take into account the dry fraction of the steam when we calculate the entropy of the stream. So the entropy of the stream is the sum of alpha multiplied by entropy of the steam plus 1 minus alpha multiplied by the entropy of the fluid. To be able to analyze this case better, let's look into the example. Okay, in this example, you see a steam at 40 bar and 400 degrees Celsius, basically this steam. Enter a high pressure turbine and expand to 8 bar. Okay, and the steam is then reheated, okay, to 400 degrees Celsius again, and is expanded again to 10 kilopascal here in a low pressure turbine. So we have two turbines, turbine number 1, turbine number 2. Calculate the thermal efficiency of the steam cycle if the specific heat of the boiler is 3000 kilojoule per kilogram. Assume the pump work is negligible and the steam cycle is ideal. Steam cycle is ideal means it's 100% efficiency. So like the previous problems, we can use two approaches. First, we can use the steam table. The second one, we can use the enthalpy entropy diagram. So let's start now with the enthalpy entropy diagram. So we know that the high pressure turbine entrance is at 40 bar and 400 degrees Celsius. As you can see here, this is 400 degrees Celsius and at around 40 bar, so slightly less than 5 megapascals here. This is basically the point of entrance of the high pressure steam. And next one, it exits at 8 bar. Okay, 8 bar is basically at this point, and then the efficiency is, it's assumed 100%, so we can find the enthalpy here. We can also get the enthalpy here. That will be enthalpy 1 when the steam when the steam enter the turbine. The enthalpy 2 is when the steam exit at the turbine at the first turbine. And then the steam then goes to turbine number 2 at lower pressure, but in between we have a heating, okay, and the condition that the steam, in this case we assign as enthalpy number 3, is at 8 bar and 400 degrees Celsius. We need to find out where is that point in the enthalpy entropy chart. That is basically the point. So we have 8 bar and the temperature now increased to 400 degrees Celsius. Exactly, this is the point where the steam enter the second turbine and exit at 0.01 bar isentropic. So we need to find out that So isentropic mean we need to pull the vertical line from this point and then find out where it cross pressure of 0.01 bar, which is at this line, and this is the enthalpy. From those data from the chart, we can then calculate the total work generated by the turbine, which is delta H of the high pressure turbine and delta H of the low pressure turbine. Okay, if you key in all of the data right, you get this value. And the total heat input is the heat input of the boiler and the heat input of the heater in between the two boiler. So you can also find out the value in this chart, and in the end we can calculate the thermal efficiency, that is equal to the work divided by the total Q. We end up with a value of 36.4%. The next approach is we can simply use the steam table, but the thing is you need a mastery of steam table to be able to solve this problem using pure steam table. So the same thing like in the previous example, when we look into the steam table, we check at a 40 bar and 400 degrees Celsius, we find out this enthalpy. And we also check the corresponding entropy at this given condition, okay, which is then 6.7 here. Then we analyze the high pressure turbine exit point, which is at 8 bar, okay, and we need to find out we need to find in the table the point where it gives you the same enthalpy as the same entropy as the entropy inlet from the turbine entrance. Because why? Because we know that in the turbine it is the process is considered as isentropy. We look into the table and then find out the enthalpy of at this point is corresponding to this value, okay, and this is basically the point where the where the steam exit from the high pressure turbine. Then after this we look again into the low pressure turbine. It is at 4 we assign that point at point 3, which is at 8 bar and 400 degrees Celsius. We look into the table, we find out this value, and the entropy of this value is 7.57. We can see it from the table. And then next we go to the exit of the turbine, the second turbine, the low pressure turbine. We know that the entropy, which is 0.4 in this case, so we know that S4 and entropy at 4 is equal to entropy at 3 of this value. Then we look into that one and we find out, if you look into the steam table, we find out that this value is actually in between the saturated steam and the liquid. So then here apply the equation. So we know that entropy at 4 equal to the degree of saturation here multiplied by the entropy of saturated steam at a given pressure, plus here is the beta is basically 1 minus alpha, fraction of the wet stream. We calculate all, then we will find out that the degree of saturation is equal to 0.9257. Based on this one, we then find out the enthalpy. So we know the alpha. From the alpha, we can calculate the enthalpy at 0.4 equal to this value. The next step is exactly the same as the one before. So the total work is basically the total work of both turbine here, and the total heat input is the heat input of the boiler and heat input of the heater. corresponding to this value, and then in the end we will be able to calculate the thermal efficiency which is equal to 36.4%.